Hey Jessica, how you doing? Can you hear me?
Hello.
How's everything?
Going all right. How about you?
Pretty good. So I was able to actually solve some of those problems you sent.
Okay, awesome.
Yeah, so hopefully today, can you see my screen?
Yeah.
Okay. Were you able to work out a few more problems? It's always good to know I think one of the steps I always say is knowing the procedure before the exam, and as much as you can.
Yeah, so I've worked out a couple of them like that. I tried to go back through, I went back through, is it I think it's 63.
Okay.
Um,
Let me take a look at that one. 63.
I tried to do that
Oh,
one.
that's the one. Did we go over that one by chance?
I think we went over it. I'm still not quite sure on it.
Okay. Yeah, I got that one. Let's talk about that later.
Okay.
I wanted to start with you remember you asked me to do a non-origin one?
Yeah.
Yeah. So if you take a look at let me know if this is kind of similar to what you've seen. If you take a look at this guy, let me just change this guy first. So here, these guys, the point charges are not in the origin.
Okay.
So I made them so that they're definitely not a part of the axes, you know?
Yeah.
So is that kind of what you're looking for?
Yeah, I think so. Mm-hmm.
Okay. This can actually get harder, but the concepts are still the same. But mainly, if you have something like this, where it's not the X or the Y coordinate is not zero, I would just use this trick. So I would use relative distance. So just use the distance formula because that's all you need, right?
Yeah. Mm-hmm.
That's all you need. All you need to get are the relative distances between the point charges.
And will you remind me of what the distance formula is? It's been a while.
Okay, here. So I'll write it down. It's just for all the coordinate, for if you have, for example, you have x1 and y1, right, for 1 point.
Yeah.
And then you have another point, x2, y2. So it's just the square root of the differences in coordinates squared. So this guy.
Okay.
And add the other, the other coordinate, the y coordinate. And that's it. All of this is square rooted.
Okay.
And then I'll send this to you, what I have. So as PDF so that you can refer back to it. You don't have to write everything down. Okay. So yeah, I would say the main thing, for example, when you're trying to find the forces, all you need are the distance formula and then the Pythagorean theorem. And the Pythagorean theorem is for example, what if you had a diagonal?
Yeah, it's your x squared plus y, or sorry, not your a squared plus b squared equals c squared.
Yeah, and then in order to get the net, for example, and this can be asked in many different ways. You could either get the force in F net 1, the force in F net 2, and F net 3. Any of these guys, right?
Yeah.
Yeah, and then I would say I don't want to do a hard one because I'm just trying to explain the steps. But you could, if they ask you to do this guy, then you always have to draw, keep in mind, when you're doing these point chart or electric
draw
field,
your
your free body diagram.
Yep.
So we'll get to that. So the very first thing first is breaking it down. And when you have this is, since you don't have the relative distances, you want to find what they are using the distance. And then so specifically for this problem, let's try to do that. So I don't typically maybe they won't give you the coordinate, but they'll give you like some type of axes, or I don't know, like one of the things that they probably give you is they'll just give you the distances, which is already good, right?
Yeah.
Yeah. If they don't,
I hope so.
if they don't give you the distances, then you could just use the distance. So it's like, okay, if they give that to me, that's good. I can move forward with the free body. If not, I'll use relative distances.
Okay.
So with what we have, like, okay, I want to get D13. So that distance is from here to here, right?
Mm-hmm.
So the top and then both of these. So I would just get, so for example, my this guy is 1, 3, right? And then this guy is 1, -2. So the x's is for the first point is 1, and the x for this third point is 1 as well. So they cancel out here. X1 minus x2. Did they cancel out, right?
Yep.
And then this is y1 and then y2.
Okay.
And then so that one, can you see my yellow, or do you want me to use another color?
Oh yeah, could you use another color? Sorry.
Okay, yeah. Let me know about those things.
Okay.
Okay. So yeah, because I'm looking at it, it's a little hard to see. So y1 and y2 and then x1 and x2.
Okay.
So that's just the distance formula applying it. And then, the y1, and this can be interchanged, right? It doesn't have, like, the second point can be like the first point. The equation is going to work either way, right?
Yeah.
And then so you just plug those in. After you plug those in, you're going to get this guy.
Yep. Okay.
Yeah, so you just do the same thing for the second point. And then so my second point is like this guy, the negative point charge. So from 1 and 2, you want the distance. You just do x1, x2 again, and then y1, and then y2. And then don't forget to square them. So the y1 difference is 0 here because they're in the same line.
Yeah.
And like if you but the x's are not. So you're gonna get this, and then this is squared. Obviously this is 4, and then you get 2. So that's how you do that. So now you have the information that you need, right?
And you do it for each side, right?
You could do it for each side. So like, for example, if you did like 1, 2, 3, you could also do that.
Okay.
It'll just be the same thing.
Same thing.
But for this problem, it's not. We don't really need it. But you could do that. Yeah.
Okay. Cool.
And the next thing there, after you get your relative distances, is to redraw everything. Like without the coordinates. So like you just have the d's,
Okay.
and then you have like the location of your point charges.
Yeah.
And then so it looks familiar now, like, because all you need for like the Coulomb's formula is just what? The k, the charges, and then the distances, right?
Yep.
That's all you need. So
Yep.
that's why you have to have like that in mind. And then what I would say is, like, how do you know what the F net is, right? At that point, is you just isolate that point that they want you to find it. They always ask you, what is the point charge, at this like number for the first one, or for this point charge. Then you'll draw this guy, and then I guess we'll just go with the basics because it's always good to talk about it. So for example, if you have this guy, right? This guy.
Yeah.
And then you want to look at this and kind of like see how the different surrounding point charges act on it.
Okay.
So for example, this guy,
so
right?
You're doing it from, sorry, 1 second.
Okay.
Okay. Sorry. So you're doing it from like 1, 3, or 3, 1 to 3, 2, or I guess it's 2, 3, 1, 3.
Yep. Yeah. So this one, like, you can do it either way. What I usually do is I just take the where I'm at and then what's acting on it.
Yeah.
So where I'm at and what's acting on. So for 1, 3, what you do is you take a look at what charge this guy is, right?
Mm-hmm.
So this guy is positive, isn't it?
Yes.
So then positive is always away. This is
Yep.
away. So away means away from this guy. So it has to be all the way right there. So it's away.
Yep.
It's like that. Right?
Yep.
And then this other guy is towards, right? Like,
yep.
Because it's negative. So it's this way. Right?
Yes.
Yeah. And it's always the point is always from here. from where you're acting at, where you're coming from, where it's asking. So it's from 1 to whatever point. And then like that's how you look at this. It's like, oh, it's away, it has to be upwards, and then this one is towards, so it has to be this way, pointing towards that guy.
So is this one asking for the charge, or sorry, the force on 1?
Yeah, you could get asked many things, like either force on 1. They could ask you a force on 2 or 3.
Okay, yeah, no, I just wanted to make sure because I was thinking it was force on 3, and I was like, huh.
Oh yeah. So the force on 3 would be different. If you took a look at 3 and then you had 1, it would be this guy. This would be 3, 1.
Yep.
And then force, and then from 2, 3, it would be this way, right? Towards this guy.
Yep.
Yeah. And then this one is a little bit harder because this is diagonal. You're gonna have a F3X and
your X and
Y. Yeah.
Yeah.
So I mean, you could just break it apart like this guy. You could just do that.
Okay.
And then that's where you apply the Pythagorean theorem, right? Like
yes.
Like point charge is just using Pythagorean theorem and then distance formula. So after you do that, this is what I'm talking about. You need to get F12 and an F13, all your components that's acting on this to get this guy.
So that's just the magnitude of the force?
Yeah.
Okay.
And this force is this is because this is X right here, right? And this is Y.
Yeah.
So like, I mean, it's not that bad. And then after that, it's just what we've been doing. You apply Coulomb's law. And then the hardest part is just figuring out what D's are. The D1 and, the D's. Yeah. And then like, how does that look? Does that seem like it's easy now?
Yeah, it is. Yeah. I needed the distance formula thing for sure. Because it's been so long since I've used it.
Yeah, I know what you mean. Yeah, I'll leave this here and then I'm gonna send this one to you. You could always just take a look at this and maybe add this to your cheat sheet or whatever.
Yeah.
Okay. Yeah, so that's mainly what you do. Those are the steps. It's just applying and it's gonna get later on. There's gonna be a question that we're gonna cover where if these are in equilibrium, then what is the D? That's also another question. Like they'll give you like there's a point charge that you have to apply somewhere, and then you don't know the distance to that, but you know that they're in equilibrium.
Yeah.
So let's take a look at those, the ones that you asked. Okay, so I think that I'll go in order because you asked I think like 6 or 7 problems, so I'll go in order. Let's take a look at number 25.
Okay.
Let me see. So 25, what's that question asking?
Let's see. No, not right. It's asking, determine the electric field at the location of charge Q and the total electric force exerted on Q.
Okay, so this one should be, let me just use purple. Oh no, purple doesn't look good. Let's look at, so this is how I drew it. So this is the guy that, the given picture.
Yeah.
And then, first of all, what do you think you should do? Like before I tell you like some of the steps, like what do you anticipate that you're gonna do?
I can tell you what I did. Well, I can just tell you.
Okay.
So this one threw me off. But so you're gonna find the distances for all the sides, which I mean it's just A, and then the diagonal is your 2B or 2A.
Okay. Yeah, Pythagorean theorem pretty much on the sides. Yep. Distances.
Yep. And then you're gonna just excuse me, plug it in for each of the individual ones. So like if the bottom left hand is, or 2 rather, you say like the force of 2 on 1, then you'll do it for 3, then you'll do it for 1.
Okay.
Or on P rather.
Yeah, P is the one that we're trying to look for. Yeah.
Okay. And
the electric field and then the force, I think. Yep.
Yep, and then you'll be able to from there you will just use the Coulomb's law or the equation.
Okay. Yeah, that's what I would do. Pretty much just those are the concepts, right?
Yeah.
you're given different scenarios of like configuration, point charges, and then you have to find what either the electric field, like that point charge, or like the force using Coulomb's law, or just definition of the electric field. Either way, there's the force there, right?
Yeah.
But like, I guess so. What threw you off on this one first?
Well, so I did this one just like the way you're talking about, and got it wrong because the way the book does it is completely different. So I have a solution manual.
Okay.
It's different.
So what was the like? At what parts is it different?
So it's different in that instead of breaking things down into your X and Y components, you still do that.
That's what I usually do, yeah.
Yeah, they kind of do that. Here, let me look at it real quick. Refresher.
Okay. Because then, like, this is pretty much telling you what is the component form. So that's like you have to get like the X and Y somehow.
Yeah. So I did that. Okay. So what it does is it somehow brings in. Oh, you do it too. Okay. I just missed this. Your sine and your cosine, and that is not. No, I did that. But
you did that one, right?
Yeah, I did that one. Yep. And
okay. X is cosine usually because it's like X, and then Y is sine.
It's sine. Yeah. The weird thing is it boils down to a factored bit and then an internal I and J component. Which is interesting. So they use a bunch of factoring, which is not how I would have solved that problem.
This is the book, the solution manual, right?
Yep. Yeah.
I would say like, does it have the same like the solution? There's different ways of getting that. Does it have the same answer?
No, because what it wants is the factored form with the two vectors for some reason.
So factored form.
Yeah.
Like not that like does it even matter if you factor it? Like I would just get because like, you're not given K, Q, and A, right? You're not given this guys, but you're given everything else. So you'll have values for your X and Y components.
Okay. And that's for part B, right?
And A and B.
Okay. So the electric field at the location, you're just finding your E, and then the others asking for the total electric force. Okay. Yeah, no, I guess what I did was wrong then.
Okay. Let's just I guess let's go over it. Just like from slate scratch. Just to see like what the steps are.
Not really.
Okay. So what did you do first?
So what I did first was found my E, E1, E2, and E3, and just plugged in the 2Q, the 3Q, and the 4Q.
What did you get for your E1?
For E1, I had KE 2Q over A squared.
KQ, and you did this? This is the 2Q, right? Or which one did you have for your 1, I guess? You could have one.
My one was my one was the 2Q.
Okay, that's what I have too. So you had K, right? 2Q over A squared. Yes. Okay, that's what I have. Yeah.
How I've never seen the constant written with the vector component before.
You could do that. Like because like it could be rearranged, right? It's just a multiplication.
Yeah. The way I did it was I summed all the X's and summed all of the Y's.
Okay.
And then tried to take the magnitude of that.
To do what?
I don't know. I don't know what I was thinking there.
Okay, it's fine. The way I usually write these things, when you have this component form, because these are all vectors, right? Like right now we're not looking for magnitude. You could, but like knowing what the vectors are, it's technically just what do you have, right? Like you take a look at this guy. You have this guy, right?
Yes.
And then which one is one? Like E1P is it should be from P, so both of them are positive, right?
Yep.
So since both of them are positive, it's gonna go this way, away, which is what we have.
Okay.
We have it going away. So you have to assume like a positive, like signage, and then so X for me is
Okay.
I is going this way.
Yeah.
So that's it. Like it's not you don't have to sum all the E's if you're doing the components. Like I want to find each one of these guys first. Each one of them has an I component, right? Maybe and then a J component. If it's like completely like horizontal, it's only an I component.
Yeah, and if it's vertical, it's a J.
Yeah. So I would not try to combine them all at once yet. Don't do that yet. Do it one by one. Okay. I know, because like eventually you are gonna combine them. Like when I get to this point.
Yeah.
I am gonna combine them. I am gonna combine them. Like
I didn't
right here.
get to that point in the same. I didn't even get to that point because I was going for the magnitude, not.
Okay, if you're gonna try get the magnitude, you need to get this guy first. Okay. Because then, if you're trying, like, so this is the vector, right? The electric field vector.
Yeah.
This guy. If you want to get the magnitude, it would be this. That's just notation for magnitude. You want to get all the I's and the J's in like one term, and so that you could just do this one, right? Like, it's just EX squared plus EY squared, right?
Yeah.
And EX is whatever is in the in front of the I, and EY is everything in front of the J.
Okay.
So like, it's what I'm trying to say is it's better to work with the components first. The components, because you have like three things happening here, right? You have like one, 2, and 3.
Yeah.
Don't work at them all at once, and then combine your I's. Get those components. After you get them, find the E by adding the components. This is pretty much just E net. This E is just E net of all of these guys.
Okay, yeah.
And then simplify so that you get one I and one J. And then when you get the magnitude, you just, whatever equation I just wrote. The E net equation.
Okay. So
because it's just this one right here.
Can we go through E2 P and E3 P?
Okay, E2.
Yeah, so okay, it's E2 because that one I'm trying to see because it's diagonal, so it has the components.
Oh, this guy. Okay.
Yeah.
Okay. Yeah. When you get that, you have to do cosine or sine. Usually that's what I would do. Okay. So like for X, for example, like this. First of all, this first part is going to be the same.
Yeah.
Right? Like for X and Y. The KQ over D, that's just your electric field equation.
Yep.
So after you do that, then for X, you have to find cosine theta and sine theta. So cosine, what is your angle here?
Angle is...
And then the way this is by inspection.
Yeah, it's like, 45 degrees. Yeah, because it's half a 90.
Yeah, so it doesn't get to you, but you can always get it from like the ratio of the sides and then treg. So I got that as 45, and then cosine, and you just simplify it.
So I guess what I did differently is I kind of split it up into X and Y components, but I didn't keep those both tied to, like for instance, I had E of Q or EQ, the equation or whatever, don't know why I said Q, but whatever X, and then I had whatever E1 is, plus whatever E2 cosine of 45 degrees is.
You could do it that way too. Let me just think first. Yeah, because if you look at, it's always about the free body diagram, right?
Yeah.
You could split this guy up. So let me just draw another one. So this is like 3P, and then you have this other guy, right? 1P. Yep. And then for example, instead of doing this guy, I could have gone like added another guy here, which would have been like 2PX, right?
Yeah.
And then this one would have been like 2PY.
Yep.
It would have been the same thing.
Okay. Yeah.
If you take a look at this one, it's just gonna be the same thing. You have this AQ2 over D2P, right?
Yep.
But then this one is what is D2P?
D2.
That would have been like that's B, I think. No. We found that out. It's right here. Which is B, right?
Yeah.
If we use what I did. Like let me see, it's this guy. See, like, what did you get for your distances? I want to ask you first.
So I got a squared for the one for the is it the sorry, I'm trying to check. Yeah.
For like the x component first.
For the x component? Okay.
Yeah. What was that one? Yeah.
That one was a squared. And then let's see.
Because it gets complicated if you split it up that way. But because then what are your distances? You could say, let me see, your distances can be. It could be. I think you have to keep it at B. Yeah. Which is
okay,
which is the diagonal distance.
Yeah. So
what did you get for that one? Is it square root 2a?
I said 2a squared.
Yeah, same thing. It's the same thing.
Okay. Yeah.
Oh, you said 2a squared?
Yeah, that's what I said.
Okay, let me see. Because you did this, right?
No, I didn't do that. That's what got me.
Oh, I see. Okay. Yeah, it has to be the Pythagorean theorem.
Pythagorean. Okay.
Yeah.
No, I immediately got that wrong. But
okay. Yep. Yeah. That's I wanted to go over that because I was like, what parts are different?
yeah.
I think it's this part because what I would do so like there's like less mistakes. I would definitely just like not split them. You could split them, but then the thing is like what distances do you need? You could just split them, but I would just do this first. Like have them y and x because it is a diagonal. It's just a component of it.
Okay. So should I just whenever I mean I've been doing it the other way because I was doing it the other way on all the other problems and it always worked.
It always worked? Okay. If that's the case, just do it that way.
Well, but see, for this problem, it doesn't. I don't think, because I summed them.
Because if you had, like, if you continue what I just said, like, so if you had this guy, right, d2p squared, then this d2p has to always be root 2a.
Okay.
But then you have this component here, this cosine theta, or like the x term, right?
Yeah.
And then this x term could just be what? The cosine theta is just 1 over root 2, right?
Yeah.
It's just 1 over root 2. So did you get that one for the x?
No, I didn't. So, okay, part of my problem was I thought I was just solving symbolically for this one. I, for some reason, didn't put together the fact that the different Q's and stuff were meant to, later be put together or factored or however you do it.
Okay.
And so I just wrote it symbolically. And
that's fine. Yeah.
And then I didn't do the cosine or sine thing together. Like I have them accounted for in the EX components, that being, E1 because it's in the horizontal, and then plus E2 cosine 45 degrees. Okay. And then
and then you just added like the sine to the x, like the j component to the x, to the I.
Yeah.
Okay, you can't do that.
Okay.
I see. Yeah, you have to every time you're summing, at this point right here, it has to be summed like x first or whatever, and then summed y next. Yeah. And then the net is always the Pythagorean. It can't be added. It's the Pythagorean of like all this guys plus this guy. So the net, like every time you do this, you always have y components and then x components.
Okay.
If there's a diagonal. If it's just regular point charts like this guy, it's in line, same line. You could just add these guys, right?
Yeah.
But if you have if you have x and y, you can't just add them.
Okay. Yeah, I guess that's what and I've done it before because it's worked before in other problems, but it is where there was a line. Sometimes I did it for ones where there was a diagonal, and I think those worked. I'm not entirely sure, but I
Okay.
believe I got the right answers for those. Yeah, this one's
Okay.
just different because it includes the vector component, and the
Yeah.
other problems I've done like this didn't.
Yeah. You know what? The best way I look at these things is looking at it as like, even if there's no vector. You know, for example, here, I'll go like for this guy, right? Like this
Yeah.
is just all in the x, right?
Yep.
But x is just what is the I component, isn't it?
Yep.
And then you arbitrarily do have a y. You arbitrarily do have a y, but this is all 0, right?
Yep.
But like thinking about the vectors, it's easier to see because all of this are just it's a field, right? It's like an electric field.
Yeah.
So a field is a vector. So that must mean the force is also a vector. Force has like magnitude and direction. It's also a vector.
Okay.
But then once you get because then like sometimes you're gonna mix up like magnitudes and vectors, and then you in magnitudes you can add them, right? But then you can't mix and match for vectors. Is what I'm saying. Like maybe think about it as like every time in a vector form.
Okay.
Does it like if you were to like kind of like follow that route and like thinking about these in vector forms, does this every time make sense now? Because if you take a look at like 1p as a vector, it's only going in the x direction. That's why. So you only have this I component.
The I component, yeah.
You always have to have the I component. So you know what you can add and what direction, because this tells you the direction.
Yeah.
And then for maybe go to like 3 because that's the easy one. It only has one, and you go to 3. This one is pointing up, so it's only in the j direction.
Okay. Yeah. Yeah.
And then the hardest part is like 2p, because then you have the x component and then the y component.
Okay.
Maybe try to like if you follow this problem and then use this like kind of like a basis, it'll help out like for the rest of them.
Okay. Yeah, I
like,
guess let's start doing it with the vector components added.
Because sometimes it like I said, like you have to know what it's asking for the electric field. That's why. And then when it's asking for magnitude, I never like in my mind I'll never jump to the magnitude. I'll find the vector first, and if it does ask me for the magnitude, I'll just take the magnitude of the vector.
Okay.
Okay. So yeah, like so that's what I would do. I would get these guys and then this guy. And then like after I have all the components in I and j, I just add them, right? And then what I mean by adding them is kind of like this. So you can like the vectors, like I and j, this I and j, these are 2 i's and these are j's. You can only add like the same way like terms. You can't add i's and j's, right?
Yeah.
So you can only add like the like terms. So that like so that like these guys don't get added up.
Yeah.
They're separated.
Yeah. Yeah.
So yeah, I guess that's what I'm trying to say. Like after you get the I components, when you sum up the e's and write the vector form.
Yeah, you still have to have your individual I and j.
Yeah, and then if you do get asked like the magnitude, let me just rewrite this so that it's simpler to see. So e of x, from this is just what 8 plus 3 root 2 over 4, and e of y is 16 plus 3 squared 2 over 4, right?
Yeah.
And then if you were to ask the magnitude, it would just be the square root of these
square
guys.
root of those.
Yeah.
Yep.
And that's the actual magnitude. You can't add these guys.
Yeah, no. I was never adding the x's and y's together.
Okay.
I was just using it for the magnitude, basically, when I did it in the component way.
Okay.
Then I realize now, obviously, that this one does not ask for the magnitude. So
it's fine. Like it's always good to like maybe extend the problem because like you
yeah,
have the field and then like okay, do you know how to get the magnitude? Some of them are asking for the magnitude though.
yeah, some of them do. Yeah,
Yeah. So like I guess that's the thing like with the electric field like just try to always find the components for or draw the free body diagram, find like the sides and then the components, and then you get write the field in component form, and then follow this equation for the magnitude. And then after that, since you have the electric field E vector, you could get just the force, right?
yeah,
Yeah. So and then this is at that point. This charge is at that point. The charge that you're using is at this point, which
okay,
I think they give that to you as a small q. So that's the small q, and then I just had that in there because there's already a q in there.
yeah, and so it squares it. Yeah, I remember that.
Yeah, so this part isn't that bad. It's and then for this you could also get the magnitude of your force.
Yeah,
And you just have to like if you had all these constants, you just have to put them together, and you had the extra q in there.
yep,
Yeah, if there's numbers, like it's always good to understand the equations first, and then if there's numbers, it's like okay, so that's how you do it.
yeah.
Does this one make
And
sense? No, it's a little and it was sometimes it throws you off, but like I know the more you do it, the better.
yeah, no, and I got really good at these, and that's why I was very surprised when I looked at this one, and I'd kind of done it right, but not really, because I was looking for the magnitude, and because you can't find the E field when you split up into the X and Y, because you can't just add them or anything.
Yeah.
It's only good for when you're wanting the magnitude.
If you're wanting the magnitude, maybe there's one that does ask that. Let me see. I think there is one.
I know there are a couple earlier in the
Oh, there is one. There's I think 45, but let's talk about that after. Let's go in order.
Okay.
Let's take a look at now maybe number 29.
Okay.
Okay. What is this one asking? Let me see.
At point at which the electric field is zero.
Oh yeah, this was a fun one. So how did you attack this one?
Let's see. Sorry, I gotta do it. So for this one, I actually watched a video on it.
You watched a video? Okay.
Yeah, because I didn't really understand what it was asking, basically.
Yeah, at first it's a little. I felt like it is so much assumption to that one sentence. It's like, how do you start this? Okay, go ahead.
No, and that's totally. I mean, that's where I'm at with a lot of these problems. Right? Is I need to recognize the assumptions with them because I feel like 3/4 of the time I don't, and that's what trips me up.
The more doing this right now, like what we're doing is very important. Like I really I actually looked at the syllabus that your professor gave, and then he really gives you guys a lot of problem sets, like the odd one, which is good. And that's why I was wondering, like, oh, you've done most of them already?
Yes. Yeah. No.
But what I'm saying is like like the better and the more you do them, the intuition just comes. It's like okay, the assumptions I'm making, I know how to make them now because I've seen these before.
Yeah. Yeah. No, and that's definitely true for equilibrium, which, I mean, obviously is not in this problem. But so I think what I might start doing is writing down my assumptions.
You should, you definitely should. Okay. Like that's what I do. That's like a lot is try to like create a bank in my head of like all the assumptions and categorize them. It's like, oh, okay, for this type of problem, what are the set assumptions I can make? Stuff like that.
Yeah. So that leads me to the question: what are the assumptions that should be made in this problem?
Okay, so for this problem, let me just go through it. So it's saying here that the point other than infinity at which the electric field is zero. So the very first thing is like electric field is zero, E net is zero, right?
Yeah.
Like that's the very first thing for given assumptions. Okay. And then for givens, obviously he gives this to you guys, right? Yeah. Q1, Q2, Q positive, Q negative. And then every time I would redraw the picture, I would redraw this picture. Mm-hmm. And then like I would kind of like set myself like different cases because this problem kind of like gives you like not too much information to determine the point. So maybe the point of doing this is like, can I give this like outside, inside, outside, inside,
Yeah.
Right? So like I give myself different cases. Either am I to the right, to the middle, or to the left?
Okay.
And then this problem is only an X problem, so it's not like a Y. You don't have to like go up and down.
Yeah, yeah.
So we could just throw out the J component. So that's also another assumption. Like just work with you don't have to work with vectors in essence. You could just work with like X's. So the very first thing I would do is test these different cases.
Okay.
And it kind of like, it's like more like a thought process. Like a lot of this problem especially is like a very much a thought process. Because like what is asking you first is, what is this X? And then this X can be like any particle that's like in case 1, case 2, or case 3.
Yeah.
But you need to figure out first which one gives you an E net of 0. No, what does that mean though? What does E net? So when you're saying, oh, E net is 0, then I immediately go to this equation, like the E equation, like KQ over D, right?
Yeah.
I think it's D squared. Yeah, D squared. So let me see. Yeah. Okay. So for this one, hold on for a sec. Yeah, it is D squared. I'm thinking about some other equation. Okay. So that one, because it's saying to you E net equals 0. So there's two things that you could do here, right? Because K is a constant. This doesn't change. No change here.
Yep.
So it's either a change in the Q or a change in the D.
Okay.
Like, depending on what your Q and D's are, E is going to change, right?
Yeah.
So that's kind of like the thought, set up cases, and then like, since it's a E net, then look at like the factors in E that will make that a 0.
So for the first one there, you're showing that
For this one, yeah.
The I guess force of the charge there, however you should say it, the charge itself rather, is stronger for that one point than the other.
Okay, so for this one, the case 1, right?
Yeah.
Like if you were to put this on this end, on the right of like all of these guys.
Yeah.
And let's take a look at like what are the relative like positive and negative forces, or like E. So the E field here, or a magnitude E for the positive, like, and this is the free body right here, pretty much, right?
Yeah.
So the free body of the E would be, I'm looking at the positive, and then I want it to be away, right?
Yep.
So this is away, and then just to talk about like the directions, and then for the negative, it's gonna be towards the negative, so it's gonna be towards this guy.
Yeah.
So what we want here, first of all, is we want something that cancels each other, right?
Yeah.
After you do like E net, you want something that's like E this guy minus E minus. Because if they're both in the same direction, then they don't cancel each other. So you'll never get like a 0. Like it's like that thought, like, okay, they need to be opposite directions. And then the other thing is the magnitudes of them, the relative magnitudes are gonna change. So for this specific one, the reason why I made this like longer is if you assess, where it is. So for example, this equation will inform you if the magnitude of E plus is gonna be bigger. So the higher the point charge. So I think the positive one is higher, right?
Yes, it is.
So the higher the point charge, and then the lower, or like the closer they are, or the lesser the distance. If you think about it, the distance between this guy is pretty short, right?
Yes.
Relative to this guy.
Yes. Yeah.
It's relative distance. So the distance to the positive is always going to be relatively smaller than the distance to the negative, right?
Yes.
So that's why I'm saying this is lesser. And then so when you increase the Q and you decrease the D, what happens? So if you increase the Q,
so charge goes up and distance.
Yeah. What happens when you increase the Q and you decrease the D?
for E.
Your E is gonna get larger,
To
right?
get larger, yeah. Sorry, yeah.
Okay.
I was trying to
So
find the E equation on there.
okay. So your E is gonna get larger. Is that something you want?
Nope.
No. So like right there and then you could probably just throw it out. So I just X this out.
Okay.
You could take a look at the negative, but it's not worth the while. It's the same thing. It's you know, you have like a larger D, and then and your Q is like a very small number. So
Yeah.
in fact, yeah. So it's the same argument. Now let's take a look. Let's take a look at C2.
Okay.
Sometimes some of these get intuitive. The more, and that's why it's always good to drive the thought.
Well, if they're going the same direction, they can't cancel each other.
Yeah,
right.
they can't cancel each other, right? Same direction. Yep. So they're just gonna amplify each other.
Yep.
So it's gonna be net. It's gonna be very large. So that's why they're saying here that this is gonna go to infinity.
Okay.
It's gonna tend to infinity. So this one doesn't work neither. So what are you left with?
Left with off to the left of the.
Yeah. So that one pretty much is this guy, and then let's take a look at this one though, like just to convince ourselves that this is it. So doing the same thought, it's to the right, and then taking a look at like the free body, right?
Yeah.
So you have this point right here, the positive force, or like field. I always think force is like, well, the positive like electric field is away. That's this way. The negative electric field is toward, so it's that guy.
Yeah.
So we're right. They might cancel each other, right?
Yeah.
And then now let's look at like the relative magnitude of the E. So a larger Q, but then a larger D though. I think the larger Q doesn't really matter, but then a larger D, because this is high, right? This is pretty like far away from relative to the negative. It's gonna decrease this guy, right?
Yeah.
Yeah. So that in fact kind of like, and then this guy is also negative, so and it's going the other way, so that might really cancel it out. So that's why your E net's gonna definitely you have a fighting chance that it might actually become a zero if you use this case. So that right there is like all the assumptions. Like there's a lot there. It's like, oh, you have to do that. It's like that. I feel like this problem is like something that maybe it could show up, but it's just if you didn't go through that process, we might not be able to solve the problem. It's like one of those problems like you just have to go through it.
Okay.
But like, does it make sense though? Like it's really just applying this equation.
Yeah. No, that makes sense.
Because like this one definitely like. When you're thinking about factors, like different factors that can affect the forces in electric field. For electric field, it would be these two guys.
Okay.
Okay, and then after that, like you can always like clean it up. So I cleaned it up by redrawing the FBD, the free body diagram, and then because I wanted to get like the parameters that I'm gonna solve for. So I just I put the parameters here. And then like I made let me see. You can make this is D1 2, right? The distance from 1 to 2.
Yeah.
I think I made this 1 at 1, and then this one the negative is 2.
Okay.
And then like you don't know this distance, right? From like the left side.
No, so you make it X.
You can make it X. I made it or like D2P, whatever parameter.
Mm-hmm.
And I made this P. And then like what else is there? I think that's it. So you have the distance. You have the distance because you need the distance from P to the negative and P to the positive. So you have this guy, and then you have this total distance 1P is going to be D2P plus D12 or X plus D12.
Yeah. Okay.
Yeah. Whichever one. So and then just because I would probably pick the one with the X. And this next one is I usually start like this: draw the free body, then look for the components. From the forces you have here, or like the electric field. So I found the magnitude of like E1P.
Okay.
and then that's just the K times the Q1 over the D1P squared, right?
Yeah.
And then, but D1P is X plus D12, or the distance between the positive and negative.
Okay.
So, and then plug in what you know, and then this is what I got. I still got an X here.
Okay.
And I guess it's good to go back to like what we're talking about. Like, so this one wants you to know what this X is, right? Such that the E net is 0.
Yeah.
So this X is what we're trying to find.
Okay.
So that E net we know is 0, which is case 3.
Gotcha.
Or the case that we chose. Yeah. Yeah, it's so some of these problems you do all the math, and sometimes in the middle you forget what's going on.
Yeah.
Yeah, so that's why writing like the given, this is the way I do it. The givens, the finds, and this is my solution set answer.
Okay.
And in the givens I put all my assumptions. And so for E2P, E2P, it's the same thing, K, Q2, D2P. And then D2P, the distance there is just X. That's how far away from the negative charge, right?
Yep.
And then so since this is a negative charge, but you want the magnitude, it's gonna be positive.
Yeah.
So and then what so that's their E2P. Those are the components, E1P and E2P. The next thing is find X. Since we have the components now, we have these two equations.
Yeah.
That have X in them, and then I think you should be able to. But and then your thing is like, what equation do I solve? Well, he does give you that in the problem. He gives you that E net equals 0, right?
Yeah. Which means they have to equal each other, right?
Yeah, and so you do have that. So just looking at it pictorially, like it would just be this guy, and you sum the x's equals 0, or e's rather, e's 0, and shows you it leads you to this guy.
Yeah.
And then you plug in everything, and then for this one, it's not that bad. It's you just go with the math, and then
and solve for X.
Quadratic, yeah, and then for I think we had a problem like this before where you had like a negative. Always, pick the one that makes sense. That's within like the parameter, and then so that's what you get, 1.821.
Would you have to use quadratic equation there?
For this one, let me see. You could do many things. You could just like maybe solve for X if you wanted to. This is what I got. I got a X squared and X.
Okay.
For your guys' exam, can you guys like use other like a calculator, or do you have to show your work?
We can use a calculator, but we still have to show our work.
Oh, it's kind of like that. Okay. Yeah, I would probably just write this equation, and then put the A's and then this guy, and then just like skip to this step just for time.
Yeah. Okay.
And that's how you do. And then it's from the negative charge, just like to go back to like where it is really, because it's asking you where's the location.
Okay. So your X is your answer.
Yeah. How was that? I think that one has a lot of assumptions.
No, I think that's good.
Okay.
That one makes sense.
Okay, that one makes more sense than the other one. Okay. This one definitely is like, I really don't like this problem that much because it's a lot of thought process.
Yeah, I know. This book really likes to do that.
I really hate physics problems that are like quantitative. Like there's some quantification, but like there's a lot more qualitative stuff.
Yeah, I hate it. It sucks.
Yeah. So you just have to go through it though. Okay, let's go to 45.
Okay.
Yeah, let's look at 45. I think we went through this one, right? We went through this guy, but let's just go over it again because I think it's important. Let me see. Yeah, this is very important. And then a few things here. Okay. Hello.
Hi.
Still here?
Yep.
Okay. Did you want to go over 45?
Um, I don't, I don't think so. I think that one's a little bit more straightforward. I think there are just a lot of things I got to memorize about it.
Yeah. Oh yeah. I did want to say I remember doing this one, but remember we talked about like why it's pointing to the left.
Yeah.
Yeah. I think I said I was gonna go back to you and like okay, I'm gonna explain to you. So the reason for that is just every time you're looking at these things, that's why it's good to have these I components. And it's the reason why it's negative is because of your charge.
Oh, okay.
It's pointing to the negative because of that charge. Negative charge direction.
Okay.
Because your rod is negatively charged, right?
Okay.
This guy, yeah, it's negative, and then the electric field is here, so it has to point this way towards it.
I gotcha.
Yeah, and then you assume like right is I, positive X. So this is the reason why the electric field in the end becomes a negative I component.
Gotcha.
Yeah, that right there isn't that bad. Like that, a lot of qualitative stuff, they could probably give you like a bunch of like non-numbers, and then they tell you like, okay, what's the direction of the electric field? How I try to like debunk those problems is the more free bodies you draw, the better you are at it.
Yeah.
Just draw a bunch of like, because the way I learned this, sometimes they say like, oh, if you can't do the qualitative stuff like by drawing the free body, and then you just like number crunching, you're really not that good because like you're just doing math stuff. You're not really thinking about the problem that much.
Yeah.
Yeah, it's like one of those things. Okay, what about number 63?
I think that's a good one to do.
Okay, let's take a look at that one. What is this one asking?
This one is asking, determine the electric field at the origin.
Okay, this one's a nice one. So again, like this one actually involves like that qualitative, like where is this pointing? So let's try to like show that first. So what I do is I usually like, for this one maybe like have a graph, and then you have this positive infinity and negative infinity, right?
Yeah.
And then like this is kind of like a free body, but this is just me doing showing what is given. So X and then J component, X and I component, and then I have like the lambda given, right? And then these guys, the lambda naught and X naught are constant. This means constant.
Gotcha. Okay.
It's a real number. It's a constant.
Yep.
And then also here, maybe you want to put in like your main equation that you're gonna use. So I think you're gonna use this because you have to determine the electric field, right?
Yeah.
So yeah, this is that component form of the electric field. So okay, that's technically all the assumptions and givens. And then what I want to find is the electric field vector, the E vector. So let's just go with our steps again. The very first thing is draw a free body. This one isn't. I mean, you could just technically draw the free body from what it gives you, because you have this rod. It's positively charged, right?
Yeah.
From X naught to infinity, positive infinity, right?
Yeah.
And I'm assuming X is to the right. That's positive.
Okay.
So the electric field here, when you're thinking about it, it's gonna point this way, right?
And why is that?
Because like in the problem, it says the line charge extends to positive infinity, determine the electric field from the origin. And if you go to I think I wrote this down somewhere, away from charge.
Okay.
Let me read this again. I was doing this earlier. The line charge starts at X and extends is determine the electric field at the origin. And extends to positive infinity, okay. I had the answer earlier. Like I was thinking about this problem. Oh no, because it extends. Everything here is like it's all to the infinity, right? It's all this way.
Yeah.
So you can't make it point towards this way because this is a positive charge, right? This is a positive charge. There you go. That was the answer. This is a positive charge, right?
Yeah.
So it has to be away. You can't make it point away this way because
Okay.
that's all infinity. It's encompassing.
Gotcha.
There you go. It's like I said, like it's a conceptual thing, but you need to know why, right? That's like if
it's going the other way because you have just entirely positive the one way, so it's going to have to go the other way.
You have a material there. You can't have a field there. You have a material there. So, like, you could think about it that way. You have like this particle that's going all the way that way. So there's no way there's a field that exists there, and the only way for a positive field to exist is it has to be away. Then it has to be in the negative direction. That's the argument.
Okay, gotcha.
Yeah. So that's the reason why, and when you draw it, then it makes more sense than like thinking about it. So after you do that, then you find the components, right?
Yeah.
I think it's not that bad. I always do it this way because, like, you know, I said, like, even if you had only the x's, write it in component form.
Yeah.
So that your understanding is correct. So the j component in this case, it doesn't have anything, so it's just 0.
Yeah.
And then what about ex? This form of like writing the integrals this way is very I would say it's very systematic because if you're gonna do this problem again in another question, but the way it's written is usually like this: the e is the integral of the d, you know, the differential, and that differential is just this guy. Hold on, not that one. This differential is just this guy right here.
Okay.
And then like, so what is d of ex? It's just your form, right? Like you could just make, because these are constants. So it's just the only thing that can be a differential is the charge, because this thing it extends, right? There's a dq here.
Yeah.
K is a constant. This one isn't a constant. So and then you know for it, because it's a line charge. This is a line charge. Your Q is gonna equal lambda L, which is kind of like what I did here. But then this is a differential, right?
So how do you know that because it says that your Q equals lambda, right? Does it say that?
That's the thing that you have to assume. You assume that one because it's a line charge. Line charge or rod. Line of charge says line of charge, yeah.
Okay.
And this is the equation for that.
Okay.
Yeah, maybe you could write that down. That's not, sometimes when you're saying these things in a line charge, and they won't tell you, you could just assume that. Like just say like this equals that.
Okay.
And then so because of that, now you have a differential for Q. So just if you apply the differential for dq, then you apply it for dl. But I'm using dx, which is just a small component of L.
Okay.
So I plug that in here, and then I put that in this guy. And then the next thing I want to do is like plug in the lambda. So this is the lambda, right?
Yeah.
And then after that, I just simplify. I kind of move all the constants outside the integral, and then I'm left with this x. So this x, you get how I got that?
So is the x squared a constant?
This is not a constant.
It's behind the integral sign. Sorry. I was thinking the k was out front.
Oh yeah. This is a bracket. Yeah, this is a bracket. Okay.
Okay, yeah, makes sense. Now, how do you get the x squared down beneath that? Is it just the?
You mean the x squared?
It's given, right?
You mean this guy?
No, I was looking at the. Oh no! Okay, I get it.
Okay, good. Okay, so yeah, and then so you just solve this integral, right?
Yeah.
And then they give you the integrand limits. So let's try to solve it, because usually sometimes when you have the infinity, it doesn't make as much sense. This one isn't that bad because it's just like a fraction. So for example, this one, after you do it, you get this integral, and then you split this up, plug in the infinity and then x naught.
And yeah, it's just gonna go to 0 because
It's just gonna go to 0. Yep.
Yeah.
Yeah. And then that simplifies to this guy.
Okay.
For EX, so this you have EY now, right? You have EY and EX, right?
Okay. Yeah.
And then now let's plug it in back to, whatever we said we were gonna do, which is this guy. Like we're gonna apply like the electric field vector component form. Like going through that process really makes you understand. It's like, okay, now this is a vector. I'm working with a vector, not a magnitude or a scalar.
Yeah.
So this is a vector, scalar, but this is component. So, you plug in all these like EX and EY components. So the EY is 0, right?
Mm-hmm.
And then this guy. How did I get this guy?
Just because it's all in the x direction.
Yeah, it's all in direction, and then it's because of this. It's pointing to like the negative. Yeah.
Gotcha.
And then because of that, then this becomes the negative.
Okay. So that's where that negative comes in. Okay.
Yeah. A lot of these, like, yeah, it's because of that free body. If you didn't draw the free body, you're like, oh, you're gonna miss like a negative sign somehow.
Okay. Yeah, that makes sense.
Yep. So that's how you do that one.
So is the electric field always going to be opposite from, or go the other way when something's positive?
Yes. If it's away, positive means away from that guy.
Okay. All right.
Okay.
That helps some too.
Let's look at. Okay, this one isn't bad. What about this one?
Yeah, this one I think it was this one where they just all of a sudden throw in the cosine.
This one's a tough one actually. So like, let's go over it.
Okay.
Let's try. What part did you like that cosine? Where does that come in? Let me see. This is kind of similar to the other one.
Yeah, I think
like,
it's just some of those assumptions again that I'm struggling with. But this one you can make a triangle out of it. Okay, so that's what I should be doing. Okay.
Yep. You should. The free body is the one that really like simplifies things. Like once you like convince yourself, like, okay, I'm drawing this. All the math in the free body seems to make sense.
Yeah.
Then you write the equations.
Okay.
And then when you draw like different things, you're drawing different things. You'll know what. This is just me doing the trig, and then this is me. Yeah, all the trig.
Okay, and then so whenever I have, because there's another arc problem like this, and it was on its side. It's the one that we went over.
This guy, I think it's the sun.
Yeah, that one. Yeah. So why is it that in that one you don't end up using? Oh, you do end up using sine.
Okay. Yep. So you want an explanation for that one?
Yeah. Sure.
Okay. So for this one, you use what you end up using is cosine.
Okay. Yeah.
And then this one is sine, right?
Yeah. Because it's your x and your y, or other way around. But yeah.
And then actually, if you draw this free body, draw it this way, and then maybe like in your cheat sheet have it this way, like draw it. It doesn't change. You always have like let me just draw this carefully. If you're pointing it this way, but this is your D and E, DE, right? This guy is always going this way. Is your DEX? This guy's DEY, right?
Yeah.
We're not even talking about any charges yet. We're just talking about like direction of.
Yeah.
But then this is away though. So for example, there's a positive guy over here somewhere, right?
So does it show it as being away, or is that again just another assumption?
Because this is positive.
Because it's positive. Okay.
Yeah, this one's positive, so it's away. This one is negative, so it's towards, right?
Okay.
Like this guy is actually negative right here, and I'm pointing it towards it.
Okay.
This one is like positive, and putting it away from it.
Okay.
And then like it doesn't matter. You could have gone this way as well, as long as it's away from it.
Okay.
And then, but after you draw this DE, you have DEX and then DEY. Same with the other guy. This doesn't change, is what I'm saying. The only thing that changes is the direction this is pointing. So this DX is always going to equal DE sine theta. and dEy is always going to equal dE cosine theta.
Okay.
If you take a look at this guy, it's the same thing, right?
Yeah.
No. So, yes, every time I always do that. EY. So you know this guy, and then this guy.
Okay.
Yeah. If you do this problems, like both of these problems actually, and then one of the ways that will make you understand it is like, you know how this arc is going from a semi, from I think pi over 2 to 3 pi over 2.
Yeah.
Maybe change it, going this way, make it go this way, make it go this way,
Okay.
and then solve those problems. But then anyways, so after you do that, then the component that you want, actually, before I talk about that, like let's just take a look at what we have first for this guy.
Okay.
So he gives you the lambda. So it's lambda naught and cosine theta, right?
Real quick. So
Okay.
whenever I see one of these problems, I should be assuming that I'm going to use either the sine or the cosine depending on which direction it's oriented.
Yep. And then we'll talk about like which one do you use in the setup
Okay.
right here. But then you should always set it up like this. It's always going to be very similar every time. Like whatever direction your point charge is at, draw something like this.
Okay.
And so anyways, so like the lambda is lambda naught and cosine, and then he gives this to you. The lambda naught is a constant, right?
Yes.
Okay. And then like r is given to you. This is radius, and then the positive charges, he gives this to you too, right? And then the p point charge, he gives that to you.
Yeah.
And then what you're trying to find here is the force field at p, right?
Yeah.
Okay. So let's draw a free body, and that's what I usually do. So like what I would do here, I'm gonna explain all these different steps. So first, typically you just assume up as positive and right is positive as well, right?
Yeah.
And then draw out like these components. So you have this rod.
Yeah.
And then like a portion of this rod is ds or dl. And then you have this r, right?
Yes.
A portion of this arc right here is d theta. You always have to do this because then you have to set up the equations.
Okay. Yeah.
And then I drew this so that I know where I'm going at. So what I would do is I'm going from pi over 2 to 3 pi over 2, right? Or yeah, that's what I'm doing. Or
yes.
You could either go this way. I think this is why. Let me see what I did here. Yeah, I went from 3 pi over 2 to pi 2.
So it doesn't matter which way you do it.
Yeah, you could even make this negative pi over 2.
Okay.
Just to be consistent. And then so I had my limits there. I drew my, the forces because this is positive a rod. So I have it going away, my electric field differential. Okay. And then so I have this guy, EX now, which is DE sine theta. And then I have this other guy going down.
Here's your DEY.
Which is this guy, DEY.
Okay. Cosine.
And then what I want to do here is like, so I have P, right? This is P. Yeah. So I have the charge of QP. Okay. And I also have the electric field away, right? This is away. So the next thing here is figuring out my free body, which is, so I have the P, I have the DQ, and then this E is going south. So it's, what does that mean? That's negative J, right? Yeah. Mm-hmm. And then let's talk about this one, this figure right here. So knowing that you have this P, you know how you have this rod that's positive, right? Yeah. So it's all positive, right? You could pick points, but it's all positive. You have one at the right, on up top, and then one on the left, right? Yeah. So let's draw the free body here. So let's, like, for example, call this 1, and then the top 2, and then the left 3. Okay. So this one is the E1 because it's pointing away, right? Yeah. From this guy. This is the E3 pointing away, and then this is the E2 away, right? Because it's positive.
Okay.
What happens with these two?
Cancel.
It cancels. So the X, there's no X, right? There's no X component.
Oh, okay.
And then the Y, what happens to the Y now? It doesn't cancel.
Yeah, it doesn't cancel, yeah.
Yeah, okay, this will make sense in a bit. So the Y doesn't cancel, X cancels. So now let's set it up. Set up the EX and the EY components. We always do that, right?
Yep.
So what was the EX?
The EX was 0.
Because why?
Because they canceled each other out.
Yeah, so that's the reasoning for that one.
Okay.
And then the other one does the same thing. You know, this one, which one cancels?
Why?
Exactly. So that's why you only have the EX, which is the what? The sign.
Okay.
And then this one, the Y is the one that doesn't cancel, which is the, what term is that one? The cosine.
The DE cosine, yeah.
Yeah. So then let's look at for EY. So you already have EX is 0. It's good to always know that one. So EX is 0, we got that. EY is next. We always write it this way. EY is the integral of DEY. We know what DEY is from our free body.
Yeah.
So we plug that in, right?
Yeah.
And we got all that, and then this is still cosine. DE,
okay.
We know DE. DE is just like, you know, like we know E. We know E is equals K, right? Q over R squared or something like that.
Yeah.
And if you take the differential, it will just be DE. It would be DE and then DQ, right? DE and DQ. Because K and R, because K and R are not part of the, you know, it's nothing really. DE, they're all constants.
Differential with respect to Q?
Yeah, because these are constant. This is a constant.
Okay, gotcha.
DQ isn't a constant. If you take a look at it, it's there's different parts. There's different parts of it. Yeah.
Yeah. Okay.
And then so after you do that, you just simplify. You have like this guy, right? You simplified it, and then you take a look at this again. This same thing you need to apply every time. This is a linear charge, right?
Yes.
So you have Q equals lambda L.
Okay.
So you take the differential of dq. Lambda is constant. In a way, it's not really a part of dq. So it's a dq is the one that is the length, which is ds.
Okay.
dq equals lambda ds, which is a portion of L.
Okay.
And then so with that, what is ds though? This is arc length, the equation.
Oh, see, I don't know that. Yeah.
Okay, so let me explain that one. So you have this as the length of this guy is L, right?
Yeah.
This is L, the length of the arc. Not the length of the arc, but the length of the rod is L. And then, but you have this R, right?
Yep.
And up to this R is just theta, right? I mean, anywhere up to this point.
Yep.
So the arc length, or L, because you bent it, is R theta. That's just an equation of arc length.
Okay, gotcha.
Which is this guy.
Okay.
So after you do that, then you take the differential of that portion of L, which is ds, and then this is actually R, a big R. So then you have the big R, which is the radius, and then the radius is constant, so there's no differential. You don't have to do the product rule, is what I'm saying, because it's a constant.
Okay.
So it's just d theta.
Okay.
ds is r d theta. So you plug this back in the differential linear charge.
Okay.
So once you do that, right? So dq becomes like lambda. What is it? R d theta, right?
Okay.
And then that's what we have here, lambda r d theta.
Okay.
And so the next thing is just simplify things. You move this lambda r in the front here. So I did that, cancels with the r squared. I got k over r, which is a constant.
Okay.
The only thing is this lambda, he gives you the lambda, right?
Yes.
So this lambda
You have to put in the, yeah, it's lambda, not cosine.
Yeah. And then so you have this cosine, lambda, cosine theta.
Oh, that's where the cosine squared came from. Okay.
Yep. Yeah. He gives you that. I think he gives that to you. Yeah, he gives that to you. But there's already a cosine in there.
Yeah, so it becomes cosine squared. Okay.
Okay, so let's take a look at this. Now the math comes in. That was just like us plugging things in.
Yes.
And then so this part becomes when the math applies. So let's take a look at it.
Okay.
So cosine theta squared, right?
Yep.
And then you know your limits of integration, 3 pi over 2 to pi over 2, right?
Yep.
Okay. Let's take a look at this. Okay. Yeah, this is a long one.
Yeah.
So the trig identity here is what you have to use.
Okay.
Trig identity half angle. Do you remember this one?
Not really, but there are so many of them. I used to have them memorized during calc, but
Yeah, I know. Like, so it's like at that point, and then like we don't know it. Same here. I just look at it after when I find it.
okay.
So one of them that applies is this guy, the half angle.
Okay.
So if you take a look at this, because you have this code, you want to do something with this guy. So what I end up doing is I made this theta over to theta. So this changes this guy, right, to theta.
Okay.
So and then when you square it, this disappears, right?
Yes.
So that's what you have. Cosine theta squared equals this guy.
Okay.
And then so that's me plugging that back in here.
So wait, real quick, how did you get the cosine 2 theta again?
So from the half angle, you have like cosine theta over 2.
Yeah.
And then this one is related to this cosine theta inside the radical, right?
Okay, yeah.
I made the one like cosine theta, I made this theta over 2 equal theta, right?
Okay. Yeah.
Yeah, so this one equals theta over 2. Yeah, and then so that's going to change the term in the radical, right?
Yes.
Because it's just twice that. So this is 2, and then this should be 2 of that.
Okay.
You could do that. I'm just saying you could do that with all the trig identities.
Okay.
Like if there's one that doesn't like seem like it applies, but if you change like the inside terms, then definitely that can work.
Okay.
And then so you have that, and the next thing is I'm not writing this. Let me just rewrite. So you take out this 1/2. I took the 1/2 out.
Okay.
Take out here, and then like you just do the integral. So it's theta sine 2 theta over 2. And then after doing the integral, like all that, you're gonna get this negative pi, right?
Okay.
After getting that negative pi, you take a look at this equation. This is the equation now because this is EY.
Okay.
You still need this guy, right? The lambda naught. You still need him. You have K, you have R, but you don't have this guy.
Oh, okay.
That's why this problem is long, because like you think you're done after this one.
And then you're not, yeah.
So it's screwing with you. So you have to take a look at finding lambda naught. So how would you do that? Like you would think, right? How do you do that one?
Yeah, I wouldn't have any idea.
So like taking a look back, like before I show you, let's take a look back at like all some of the assumptions that we made, where lambda might appear, right?
Yeah.
Do you remember this guy?
Yeah.
He has lambda in here, right?
Oh, so you can solve for it.
So if you did this on dq equals like lambda ds integral q lambda y ds, right?
Yep.
So that's what I got that. That's how I got that.
Okay.
So you plug in lambda naught, lambda naught times cosine theta, pretty much.
Mm-hmm.
And then like you plug that in here, right?
Yep.
But this ds, what is ds? We know ds from what we did up top.
Yeah.
From the arc length. So we just bring that down, nothing new. You plug it in, r d theta, and then you times these guys. After timesing them, you get this guy, right? And then this other guy after rearranging.
Yep.
These two are constants.
Yeah.
Yeah. The only thing here is cosine theta d theta.
And that's just sine.
And then in the end, you get this. And then what is that? Yeah, it's a really good, it's a really messed up problem.
Yeah, it really is. He said he'd make the integral problem easy, so I don't think he will do this one.
He won't. Okay, but as long as you, it's not that bad after like you go through the process. It's like it's probably the one nice thing is if you know this, you know all of them, I guess.
Yeah, so I'll definitely work with this one a bunch.
So because it takes you through all the whirlwind steps that you have to do. So after you do that, you have this lambda knot. So okay, you just do that, and then like, oh, okay, you're giving this guy, you're giving that guy. So that's what you have, lambda knot.
Okay.
And okay, now we're back to our old thing. After that, because we were gonna do that, but we just didn't have lambda knot. Now let's go figure out the electric field at point P. So it's EX, I, EY, J. You know this was 0.
Oh, yep.
We only have a Y component.
Yep.
This one canceled, right? This one canceled, and then this one didn't cancel. And then so we plug this in the EY, and then all the terms we know it now. We have all those defined.
And say okay, yeah.
That's it. And then like for this other part, you just times it by the QP at that point. At the point, yeah. And yeah, then you find out that it's negatively charged.
Okay.
What do you think of that one?
I think I'm just gonna have to write that one down a lot and really drill it into my head, because if I do that, eventually I will start to understand it.
It's like one of those, yeah. It's like if you remember, like was it in mechanics 1 or physics 1? There's those different assumptions from like F equals ma. It's another one of those things.
Okay.
There's like a process, and then you just have to do it.
Yeah.
It's not that bad. Like no, at least this one. Let me look at the next one. What's this? This next one is it's a little weird because like it didn't have the same answer in the book, I think. Or did you do this one?
I think so. Which 73?
Yeah.
No, I looked it up again.
And what happened? Yeah, like I was trying to compare it with like the book, the way that, or like how other people have done it. How did you do this one?
Let me see if I did it.
Because this is a good problem as well.
Well, I've got one that's similar to it. That's 79 or 77.
Okay. 77.
For that one, it's like the same setup.
Okay, let's cover this one first, and then let me take a look at 77.
Okay.
It's very similar. You would probably do the same thing as what I'm doing here.
Okay.
So actually, yeah, I'll do this, and then I'll send you the solution to 77 after.
Okay.
Because I'll send all this to you. Anyways. So for 73, let's look at 73. So you know how we have this guy?
Yes.
So what is this one asking? So like, the assumptions that can you make? It's equilibrium first, right? That's what it's saying.
Yeah.
So that means that you're what? What does that mean?
In equilibrium, it means the two are both the same.
Okay. So forces or like electric fields they're pretty much the same or like equal. The net of them is 0. And then so L, he gives that to you as well. And then the M1, I think for this guy, I'm making this M1. Okay. And then the M2, the charge there are these guys. You're given the charges and then the masses, right?
Yeah.
So like this is just me like thinking about the problem. So like I think he give you what the. So when you do these things, you should always like split this, kind of similar to like what they did at 77. Like if you're not given like the theta, and then you're given a triangle, split them up like this.
Okay.
And then like, you have a D here, which you're trying to find. This is what you're trying to find.
Yeah.
And then so you're also given that you have this this tension force, right?
Yep.
Tension is always like, since you're pulling it, it's coming down. It's always away, right?
Yeah. Yeah. Mhm.
So it's oh shit, I hate it when it does that. So it's always away. And then so you want the components though, right? So T up, T right. So T cosine is theta, right? Is up, and T sine is because theta is here. This is theta, that's why.
Yeah. Okay. Yeah.
So that's why the X is sine, T sine, and then the Y is T cosine.
Yep.
So the next thing is you have this weight, right?
Yep.
So that, and then let me see, and this one applies to this guy as well. But the very first thing, so oh yeah, I have to explain this. So you know how like you have this triangle?
Yeah.
And then this one is what, D over 2? And this one's L, the hypotenuse.
Okay.
So this is what, if you do the Pythagorean.
Oh, minus D over 2, yeah, squared. Okay.
And it's minus because like this is the Pythagorean pretty much. L squared equals D2 squared, plus this guy, right?
And why is it D over 2?
It's D over 2 because, like I said, you have to split it.
Okay, so you're solving for, okay, gotcha. So it's saying,
when you're doing these problems, like you're splitting it because you have theta in here. You have theta
yeah.
in here. Split it in the middle, and then like, if you did, you don't have a relationship. That's why I was like, you can apply the Pythagorean, right? Because it's not a right triangle.
Yeah.
You need a right triangle. That's why you have to split it. If you worked with this guy, which is this, and then you have D here, well, you can't really work with that one. You don't have a relationship. You need to have a right triangle. That's why you have to split it.
Okay.
So after you do that, same thing. Free body. I like this one because it has like forces now. So you have the Y and the X, and then you just whatever you drew here, like from the assumptions, just kind of like simplify it. So you have the positive charges, right, T sine, up, T cosine, Coulomb's force left, and then W going down, right?
Yep.
And then this is going away because it's positive, right?
Yeah. So okay, never mind. Yeah.
Yeah, if it's negative, it's gonna be going to this guy, like along with the T sign.
Okay.
Well, he gives it to you in positive, so that's why it's away.
Okay.
So you set up the equations. And a lot of this is setting up the equation and just going through the process, right? And then, I kind of drew something similar to this already.
Yeah.
And so, try to get like a tan theta. Like try different things. Maybe you can get a sine theta, or cosine theta, right?
Yeah.
But then I think the one that will work is tan theta, because you have the sine and cosine here. That's why somehow. You have the sine and cosine, so you could just combine them. So if you did tan theta, you just do like D over 2 over the other leg, right?
Yeah.
So after you do that, you just leave it be, because I want to see if something happens with the other when I apply Newton's law. So f of x, T sine, and then the other guy, cosine equals mg, and that's just applying the Newton's law.
Okay.
And then from comparing these two, I find like there's a sine and cosine here, and there's a tangent. So why don't I just divide this, right?
Yeah. Mm-hmm.
Because T isn't given, I think. Yeah, T isn't even given to you. So after that, sine over cosine, you get tan, right?
Mm-hmm.
And then you do the same things to the other side, and then you just do the math. The one thing I would do with this problem is like, there's a lot of the D is like, it's hard to like put them together.
Yeah.
So I would just plug in what I know and then rearrange.
Okay.
Instead of like trying to simplify, it's really hard to simplify something like this.
Yeah.
So I'll plug in what you know, do the math, and then from what I saw, like I got a different D from the book.
Huh.
Yeah. Try solving this. Maybe I did like look at this. Like try doing this on your own. And I tried to solve this equation right here.
Mm-hmm.
And after solving it, I didn't get like it's similar numbers, but like it's off by one magnitude.
Huh.
Yeah, it's off by one magnitude. So, like I said, book is wrong.
Okay. No, they do that sometimes, I think, too.
Yeah, it's one of those things like you never like try to do the problem, apply the principles. Most of it is right,
Mm-hmm.
but like never always trust the book. Like try to like I said, figure out a procedure that works every time. So, and I think this always works. Free body, components, and then after that, the electric fields, and then the forces from the electric field.
Okay.
And a bunch of stuff. Yeah, so I'll try to send this to you and all of these in PDF. And then 77, I can also send you that one. I'll do that like right now after this.
Okay, that sounds good.
Yeah, so what do you think? Does it make more sense now?
Yes, it does, yeah. Especially the derivative ones. Because
Yes, yeah. Those ones like it's really just setting it up. Like cuz there's a lot of drag there too, like which one cancels, like which one do you do?
Yeah.
And then the assumptions. Okay. For chapter 24, do you want to do some practice next week before your exam?
Yeah, definitely. I'm probably going to need a decent amount of help on it. So do you want to do Tuesday? Does that work for you?
Yeah, let's just let me know what time.
Okay.
I think right now I don't have any other person on Tuesday. And then for chapter 24 problems, like, do the same thing. Just send me the ones that you want, and then we'll talk about like. Did you do any of them yet?
I haven't gotten to them, no.
Okay. Yeah, like I'll try see if I can like just look at the assigned chapter 24 problems.
Okay.
And then if not, just like send me the very difficult ones.
Okay.
Cool. Jennifer, yeah, I think that's pretty good. Thank you for going through it. I think this process is pretty. Do you like this rather than just like going over the problem on check?
Yeah, I think so. Yeah.
Yeah, I do this most commonly. Like I the way I do things typically is like this. Like I just didn't have enough time. Usually, if I have like
first time
2 to 3 days prior, then I can prepare something, and it's more effective because like okay that. We can grind to like the process of doing it, the math and assumptions.
In the future, can we go through the problems step by step? And by that I mean, can we do them at the same time? So like, actually go through and do the problems.
Yeah, we could do that. Actually, do you want to? What I can do is I'll send you the solutions, and then I'll do them on the spot, like for 24. Did you want to do that?
Yeah, I think that'd be helpful. Yeah, I think that'd be helpful.
Okay. Yeah, just send me the challenging ones, and then so I can like look at it first, and then we'll I think it'll be good that way as well. It's just like the time it takes to like write it.
Yes, yeah. Yeah, but for some reason I feel like that always just helps. Just writing it, the act of writing it, I feel like.
Okay. We can make that work. Yeah, I'll do that for the next one. Cool.
Okay, that sounds good.
Okay, have a good one.
Thanks, you too.